dark matter and also naturalness problems in some of models at SUSY. And so today it's going to tell us about, of course, we all know about the Higgs mass result, and the Higgs couplings and the naturalness in the Lambda-SUSY model. Thanks. Let's welcome our speaker.
Thank you very much, and thank you for that introduction. So yeah, as you just heard, this talk is going to be about Higgs and naturalness and supersymmetry. So you can kind of get an idea of what this talk is going to be about. I'm sure you've heard a lot of things said over the past few years about these things and how they fit together. So here's one more talk. Hopefully it's not too boring. This talk is based on this paper that I recently finished with people at Cornell. So Margot Farina is a postdoc at Cornell. Maxine Perlstein was my PhD advisor. And so we've been working on this for the last year, and we put it out last month. And I will try to tell you about what we did. So we've had, so this top says life after the Higgs, right? And so we've had the Higgs for a few years now. And so the initial excitement of looking at plots like these and seeing that this was evidence for the long sought after Higgs boson, it's a thing of the past now. Right? So we've lived in that glory. We've got our Nobel Prize, and now we're back to reality. And the reality is that we are finding ourselves in this so-called nightmare scenario, right? So we have the Higgs. Unfortunately, we don't have anything else. And the Higgs looks exactly like the Siano model Higgs. So it might just be possible that this is all we have, and the LHC is not going to find anything else, right? And so this is the conundrum we find ourselves in. We found the Higgs, but it's not the kind we were hoping for. We were hoping for some deviation from what the Siano model predicted the Higgs to be, and unfortunately, we have not seen any clear evidence of that yet. And that means that all our theories of things like supersymmetry are in trouble, right? And so let's look at what supersymmetry, what the status is right now. So the most natural versions of supersymmetry tell us certain things about the Higgs, right? So they tell us that the Higgs mass should be close to the Z mass, the weak scale, and that because there's more than one Higgs in supersymmetric theories, now we expect some mixing, and because of that mixing, there might be some deviations from Siano model-like Higgs properties. So that's what supersymmetry theories would generically tell us. Of course, reality is something quite different, right? So the reality is that the Higgs is in fact significantly heavier than the Z mass, and their properties are exactly like the Siano model Higgs properties, and there's not much deviation in the Higgs properties. So that looks odd, possibly disturbing. In addition to the Higgs, SUSY theories tell us about other particles, right? So they predict this whole bunch of superpartners that should be observable at the LHC. In particular, naturalness tells us that Higgsinos have to be light. They can't be too far above the weak scale. Stops have to be light in order not to make electroweak symmetry breaking unnatural, and gluinos have to be light for the same reason. And so all of these particles supposedly should have been discovered by the LHC already. And reality is that there's no sign of any of these, right? In particular, the stop bound is currently at around 700 GeV, and that's very, very disturbing. Of course, there's more things that SUSY theories contain, right? So in particular, they contain candidates for dark matter. And so if your SUSY particles are giving you dark matter, then you might maybe expect some other signals in direct detection or indirect detection. There's no sign of that either, right? So Xenon 100 at the time I started writing this talk, but now Lux is the strongest bound setter on direct detection cross-sections, and that cross-section is actually cutting deep into this parameter space that SUSY predicts. So this is the general state of the community, right? So this looks very depressing, and there are all these problems, and we have no idea what to do with these. And maybe naturalness is maybe not a good criterion, and maybe it's time to give up on this notion that things might be natural. However, when you really go back and think about these things, right? So you go away, meditate on these things, and then you have this deep intuition that fine-tuning is somehow very perverse, right? You want things to be natural. They have to be natural. If they're not, then somehow we're not doing physics correctly, or it's not worth doing correctly. And like Einstein said, right, nature is not malicious. It can be subtle, but malicious it's not. And so going back to this picture, maybe we should not give up on naturalness yet, and this is maybe not the correct attitude to take. And despite this picture, we have to be strong particle physicists, and we should not see things as depressing, right? We should see things as interesting, and we should not see problems, but rather we should think about these as opportunities for exploring new ways of writing down theories of SUSY that are natural. So with that philosophy, let's move on and go back to what the main problem was with regard to naturalness, right? So with naturalness, the issue is that we have a mass scale. The mass scale is the weak scale, right? So we know what the Z boson mass is. We know what the W boson mass is. And in SUSY, these masses come out of the minimization of the Higgs potential. So the Higgs potential minimum gives you a value for the vacuum expectation value of the Higgs. That in turn gives you the Z mass, and that number is known, right? That number is known, and if this number is to pop out of the theory naturally, that means that these numbers on the right-hand side should not be too far above the weak scale, right? So if these are all TeV scale numbers, then the fact that they cancel down to give a number that's less than 100 GeV looks unnatural. So it's like you handpicked your numbers to give you the right outcome, which is not what we want of our theories. Right? So naturalness tells you that the mu parameter and the uptype Higgs mass parameter, they should all be close to the weak scale. And one way to measure how fine-tuned this relation is by measuring the variation of this output number, the Z mass, with respect to variations in the input numbers, right? So this is the Barbieri-Giudici measure of fine-tuning, which looks at how much the Z mass changes when you change your input parameters by a little bit. And if that number turns out to change by a lot, that means that you were relying on some kind of cancellation to get that number in the first place, and so your theory is fine-tuned, right? And so that's the measure of fine-tuning that people use, and that's the measure that I'm going to stick to. Okay, so the problem then is that in the MSSM, right, the Higgs mass is bound to be below the Z mass, but since the days of Lab 2, we've known that the Higgs mass is actually not lighter than the Z. It's actually heavier, right? And so then this problem had a straightforward fix. The fix was that you have loop corrections from stops, which can be significant. So once you add that, then the Higgs can naturally be heavier than what the observational bound was. So it was somewhat of a problem, but there was this solution, right? And so the solution was to have corrections from stops and make the stops heavy. So if the stops are around TeV scale, then the Higgs mass can easily be 120, and that's how you make your Higgs heavy. Except that gives us the famous naturalness problem, right? Which is that TeV scale stops are problematic because stops also feed into the running of the uptype Higgs mass. So if you look at the RG running of the uptype Higgs mass, you have this relation, and the outcome is that if you set your stop masses to be at a TeV scale, then the corrections to the uptype Higgs mass is also of the same order. So you have a TeV scale correction to some number, and so you have a TeV scale number going into this relation, and you want a number out that's less than 100 GeV, which means that numbers are fine-tuned against each other, right? So this was the heart of the problem with supersymmetry and heavy stops. Sorry? This is the topic level, so 1. And so this itself tells you that supersymmetry is in trouble, right? So either we have something that's inconsistent with observations, or we need numbers that are fine-tuned with respect to each other at worse than 1%. And so we need something out of the ordinary to swoop in and save the day, right? And so we stare at this hero that comes in to save the day, and we see that it has this label S, and S, of course, stands for singlet, right? So you add the singlet to your minimal SUSY model, and you get this NMSSM model, the next to minimal supersymmetric model, right? So you're taking the MSSM and you're extending it by a gauge singlet superfield, and so the superpotential contains these terms. There's the singlet doublet coupling with a coupling strength lambda, and there is the singlet self-coupling with coupling strength kappa. And the nice thing happens when you add this is that your Higgs mass gets an additional contribution, right? So in addition to this old number from the MSSM, you also have this additional term in the Higgs mass. And so if lambda is fairly large, meaning around 0.6, and tan beta is strong enough that this remains significant, then you only need a minor correction from stops. Most of your Higgs mass comes from tree-level contributions, and so from sub-percent level fine-tuning in the MSSM, you can go up to 5% tuning in the NMSSM. So clearly this is an advantage.
So this really means that what you're doing is you're adding a singlet. You're adding a singlet so things aren't tuned
Right.
too much.
Well, you're adding a singlet, and eventually, because of that singlet in the Higgs sector, your Higgs mass turns out to have this additional term, and because of that, it helps beat that fine-tuning problem. Yeah.
So in some senses, it's just a change of one type of problem for one classification of a type of a problem for a different classification.
How so?
And one is I don't like numbers that had to come out just so, and the other is I don't have enough particles, so let me add some.
Sure. Yeah. Yeah. So what's more natural, adding particles or tuning your numbers? So that's the trade-off.
Sure. How will we add particles?
That's the theorist's most obvious trick, right? You add more particles to solve more problems. Right, so the key player here is this lambda parameter, right? So this parameter needs to be large. If it is, you have an additional tree-level contribution to the Higgs mass, and then you don't need these large corrections from stops, and so you don't need a large cancellation in the Z mass, and things are more
What
natural.
other particles do you get with the singlet?
So, I mean, it's a superfield, so you have a CP odd Higgs, a CP even Higgs, and a single fermion. That makes this a dark matter with neutralinos.
So these are in addition to the MSSM?
This is in addition to the MSS.
You're going to have how many Higgses total?
Well, two more, right? So one CP
Six.
and one CP odd extra.
I mean, another CP odd. These would
One
all be
CP
very
another
large
CP.
mass, presumably?
You have to make sure that that's the case, right? Right, so that's the new.
Are there any conservation laws that come with this, or is this just an extra part of, is this extra
I
particle
think it's just an extra
content?
particle content. Right, so that's one way to fix it. Turns out that you can crank up this lambda parameter infinitely, right? So at lambda equals 0.75, you hit a lambda pole below the gut scale, which means that if you want your theory to be valid all the way up to the gut scale, you should not cross beyond this cutoff. But of course, it's not a given that this theory has to hold all the way to the gut scale, right? So maybe it hits a Landau pole below the gut scale, but maybe before that some other theory or some other particle content comes in and fixes the problem. So what you really, really know is that there cannot be a new particle below 10 TeV, otherwise there's problems with electroweak precision tests. So what you say is that I'm okay with getting a Landau pole above 10 GeV, even if it's below the gut scale, because I can imagine some other theory coming in and fixing that problem. All I know is that there's definitely no such thing happening below 10 TeV, because electroweak precision tests constrain that very strongly. And so if you take that attitude, then you can actually crank up lambda all the way up to 2. Right? So you have this new parameter range that is open to you if you allow a Landau pole somewhere. And you think of this as an effective theory that's only valid below 10 TeV. And this extension of the lambda parameter is what's known as the Lambda-SUSY model. And if you have a large lambda coupling, then it's very, very easy to get a 126 GeV Higgs, even at just tree level, no loop corrections needed. Right? And so here's a plot from this paper that was very highly cited. So Lawrence Hall, David Pinner, Josh Ruderman at Berkeley analyzed the Higgs in the context of supersymmetric models, and their conclusion was that in the MSSM things are very fine-tuned to get that mass. In the NMSSM, fine-tune is 1 part in 20. If you go up to Lambda-SUSY, so if you crank up this lambda parameter, then you can get the right Higgs with a very small fine-tuning. Right? So you can see that, so the blue contours are the Higgs mass, so there's 125. The red contours are the amount of fine-tuning that's needed. So if you have a large lambda, then you need a fine-tuning only of around 5 to 10. Right? Whereas if you live with a small lambda parameter, then you need significantly higher fine-tuning. So their observation was that Lambda-SUSY makes the 126 Higgs mass more natural. And this idea actually goes back, this idea of Lambda-SUSY actually goes back to this paper back in 2006, right, where Barbieri, Hall, Nomura, and Richkoff came up with this idea that with this large lambda coupling, you can have Higgses that are naturally very close to 300 GeV. It's a very straightforward application of this idea. And so that is a natural explanation of why Leb had not seen any Higgs bosons at that point. Right? And so they labeled this framework Lambda-SUSY, and so that idea had been around since then. And so now that the Higgs was found at 126 GeV, people started looking at that again. So you might wonder at this point, right? So this is giving you Higgses at around 300 GeV. So if Higgs was found around 300 GeV, then this would be exactly the right framework to work in. But given that the Higgs is not that heavy, right? It's only 125, which is a far away from 300. Is this still an interesting or a useful model to look at? And the answer when I started looking at this model that I ended up with was yes. This is still a very, very interesting model to look at, because this benefit of raising the Higgs mass is not the only benefit of Lambda-SUSY. It comes with other perks, right? And the most important of those other perks is that
300 GeV
yes.
Higgs in this Lambda-SUSY is less fine-tuned compared to 126 GeV.
Yeah. So if lambda is 2, right, V is 175, then
So
lambda V is 350, and that's the scale.
So
for-
that's what it's natural.
Yeah, and I'll have more about that later. Yeah, so an even bigger benefit of Lambda-SUSY, it turns out, is that not only does it gives you a heavier Higgs, but it also makes heavier superpartners more natural. Right? So it helps reduce fine-tuning with respect to heavy stops, and that is actually a bigger problem these days, right? So not only just the Higgs mass, but the fact that we have not seen any superpartners. In fact, the fact that stops are now seemingly close to the GeV scale rather than a few hundred GeVs, that is far more natural in Lambda-SUSY than in the MSSM or other models of SUSY. So let's look at how that happens. Right? So let me remind you of what Lambda-SUSY does. This is the extension of the superpotential, and so in the Higgs potential you have the soft masses, you have these trilinear couplings, so A lambda that goes with the same structure as lambda, A kappa that goes with the same structure as kappa, and that's it, right? So the new parameters that you're introducing are A lambda, A kappa, lambda kappa, and the soft masses for the three fields. And there is no explicit mu term, right? So that's a big difference between the NMSSM and the MSSM. There's no explicit mu term. The mu term comes about when the singlet gets a Bev, and in this way, it also solves the mu problem of the MSSM of explaining why the mu parameter is so small. And so that's an added benefit that's still there. And so this is your parameter space, right? And if you take this and then go back to this natural problem of the Z mass, then what's really happening here is that this relation comes out of the minimization equations of your Higgs potential, right? So your vacuum sits at the minimum of the Higgs potential. At that minimum, these are the relations that have to be satisfied. And if these relations have to be satisfied naturally, then the Z mass, which is GV, has to naturally be the same order as the mu term and the uptype Higgs mass, right? So that's what not fine-tuned means, that they are all around the same level, and you don't need to actually tune them very closely to get the right number out. So that's the MSSM. In the NMSSM, things are slightly different, right? So this relation is still true in the NMSSM and Lambda-SUSY, but your Higgs sector is now an extended sector, right? So you have the singlet superfield, which means that your minimization equations are going to look completely different. So in addition to the uptype and the downtype Higgses, you also have the singlet, which gives you an additional equation that needs to be satisfied, right? And so this is a completely different structure. And if you stare at it more closely, then you realize that, so for example, this term, this term, this term, they're all there from the MSSM. But in addition to this usual Z mass, right, G squared, V squared, which is the Higgs Bev, in addition to that, you have this new term in Lambda-SUSY and the NMSSM that was not there in the MSSM, which goes lambda squared, V squared, right? And so your most natural spectrum in this case then means that it's not GV, but lambda V that has to be the same scale as mu and the uptype Higgs mass, right? Same argument, slightly different set of equations, but it's the same logic, right? But then this tells you that the natural scale for the electroweak scale is lambda V, not GV, right? So what Lambda-SUSY essentially does for you is that it raises your weak scale. So we are so used to thinking about the weak scale as the Z mass, right? We're so used to thinking about it as 90 GeV. but that's not necessarily true. We know what V is, but it's V up to some order 1 coupling, right? And that coupling constant can be different from G. In fact, in this case here, this is a particular realization of the case when it's lambda V rather than GB, right? So your weak scale in this theory is lambda V, and when lambda is 2, lambda V is 350 GeV, not 90 GeV, right? So your weak scale is actually higher than what it seems to be. And of course, this means that compared to the MSSM, if you calculated fine-tuning the same way, then your fine-tuning measure will improve by this factor, right? So lambda V over GV squared, because it's the ratio of the mass squares that gives you fine-tuning. And so you've improved your fine-tuning measure by this factor, right? So if lambda is 2, G is around 0.5, 0.6, so this number is bigger than 10, right? So you've gained an order of magnitude, larger than an order of magnitude in your fine-tuning measure. And what it means for TV scale stops and Guinos is that these are worse than percent level tuned in the MSSM, right? Because this TV scale is 2 orders of magnitude larger than the Z mass. But then in Lambda-SUSY, it's only 10% tuned because your weak scale is actually higher than what you thought it was. So these numbers are not too far from the weak scale, even if they're at the TV scale. And so this really is why, so this really is for me this was the most fascinating thing about Lambda-SUSY when I saw this. And so I thought I would spend some more time looking at it. I should also mention that Lambda-SUSY is also more natural with respect to dark matter, right? So so here is the usual plot, right? So cross section, spin independent scattering cross section across the dark matter mass, and these are the bounds from the various experiments. So xenon 100, xenon 100, the latest one, and then the projection for the 1-ton experiment. And so I've scattered some points with color codes reflecting the amount of fine-tuning you need to sit in that point. And so in the MSSM, you see that, so red is the most natural type of points, green is more fine-tuned by an order of magnitude, blue is more fine-tuned. Right, so here in the MSSM, you see that all the red points are sort of in the upper left corner, and most of it is ruled out. In the NMSSM, they further migrate to the right, and some of them manage to go down below the xenon bound. In Lambda-SUSY, right, all across the board, across all masses, you have all these red points that creep below the xenon 100 bound, which essentially means that there are points with these low cross sections that are only 10% or not even 10% fine-tuned with respect to electroweak symmetry breaking. So in that sense, Lambda-SUSY will also give you a more natural explanation of why we have not seen anything at direct detection. Right? But that was just an aside. So this is something that we looked at a couple of years ago.
That means that if you consider there's going to be no signal from these direct detection experiments, even for Lambda-CM models, there are also going to be those yellow points, which means there are a lot of fine-tuning still there.
Right. What about it?
I'm just pushing down this direct detection experiment to limits, but making a model more fine-tuned.
Yeah. And then, of course, the interesting number to look at is the 1-ton bound, right? So the projection is that it's going to go down all the way to these red lines, and in all 3 models, that's going to probe all variations of SUSY at 1% level or better, right? So unless it's tuned to worse than 1%, you'll probably see some signal at xenon 1-ton. Right, but forgetting about dark matter, right? So that was just an aside. So back to the Higgs, right? And so now we have a framework. We understand that a 126 GeV Higgs can be more natural, and electroweak symmetry breaking can be more natural. So how do you actually go about getting a 126 GeV Higgs in Lambda-SUSY? Right, so this is what the mass matrix looks like. And so I'm working in the basis where my first entry is the Shannon model like Higgs, right? So if it were exactly that, then I would get exactly what looks like Shannon model Higgs in all ways. The second entry is the orthogonal component of the Higgs doublet, right? So whatever is not in the Shannon model Higgs is in that component. And finally, there is the singlet Higgs that the singlet superfield introduces, right? So there's 3 Higgses, they can all mix together, and the eigenstate, mass eigenstate, is going to give you your Higgs bosons. And so the story is, like I told you, right? If lambda is 2, tan beta is order 1, then this number, the 3-level mass before mixing, is 300 GeV, or 350 GeV, right? Too heavy. And so you have to fix this somehow. And people looked at it, And they decided that the easiest way to fix it was to have it mixed with the singlet. And when that mixing happens, then you have what they call this pull-down effect, and it pulls down the Higgs mass from 300 GeV to 125 GeV, and that's fairly easy. And so this is work done by some people at Maryland. Right? So the Maryland Theory Group looked at this, and they saw that this was indeed possible, but they also saw that because you have to cancel such a big number down against this off-diagonal mixing term, which also needs to be big to get a number that's eventually a lot smaller than these, that itself requires a fine-tuning of parameters. So that itself requires 10 to 15% fine-tuning. So it's possible, but it comes at a cost, a fine-tuning cost. It's not that bad, but it does come at a fine-tuning cost, right? There's no natural way to get them to mix and get that mass. Of course, you can crank down the value of lambda, but at that point, you have to worry about the singlet being too light, and then, of course, you lose the fine-tuning improvement with respect to stop masses, right? So I'm not going to think about this other regime. I'm going to stick to the case where lambda is 2 or close to 2 and see what happens there. So that was one observation. Another group also looked at the same thing and found something similar. Right? So this is Tony Gargetta's group at Melbourne. So they also looked at the 126 GeV Higgs in the context of NMSSM and Lambda-SUSY. And what they also found was that this is how fine-tuning goes with respect to the exact value of lambda to get the 126 GeV Higgs, right? So the most natural way is to get the tree-level mass to be at 125. If not, you can have the tree-level mass be larger, but you need to cancel it. You need some fine-tuning, so there's some fine-tuning cost, but you can have any value of lambda, and larger values of lambda are also possible, right? And another thing they also pointed out was that tan beta is now also constrained if you want to live in this limit. So if lambda is large, if it's close to 2, then tan beta cannot be larger than 4. Otherwise, you run into problems with electroweak constraints again. So if you want to live in large lambda regime, then you cannot crank up your tan beta, which is too bad, because otherwise, if you just crank up tan beta, that was one way of getting the Higgs mass, tree-level mass down. Right? Unfortunately, you can't do it, so you have to live with this cancellation between large numbers to get 125. So that was the picture with Lambda-SUSY, right? So 125 GeV Higgs was possible. It needed some kind of cancellation, but you could get that mass, and so you could get all these benefits of improved tuning with stops in Lambda-SUSY. Of course, we have something else to play with now, right? So we are moving on to this next stage, where not only do we know what the Higgs mass is, but we have more information about the Higgs. We have more information about its different couplings to different particles, right? And so we have all these different measurements. We have their ratios, and they're fairly well measured. So the question I would like to ask now is, does this change the picture? Is there any other caveat that comes into this? Is it more fine-tuned? Is it natural? How does this change the picture? Right? And so going back to the Higgs mass matrix, you see that they're all given by the same terms, right? So there's V, there's the singlet web, there's these A terms, and so they all feed into all the masses, which means that if you just started throwing points in, then you would always see that they are of the same level, all these masses are of the same level, and therefore they have to mix. Right? So generically, you get a lot of mixing in the Higgs sector in Lambda-SUSY, which means that any given eigenstate would have some significant fraction of all three of these ingredients. So let's think about the 126 GeV Higgs as being some linear combination of those three, right? And so what we can use the Higgs coupling measurements to do is that we can constrain the amount of mixing with this heavier doublet and the singlet, right? So we now know that it has to be very standard model-like, which means that this is going to be the dominant component. And what we can try to do is look at how much of it can be this guy and how much of it can be this guy. So I'm going to define D as the fraction of this doublet and S as the fraction of this singlet. And the Higgs data can be used to put constraints on those terms. And so we ran the fits, and this is what we got. Right? So the green and yellow are at 2 and 3 sigma levels. And so what you see is that D is very, very strongly constrained. Right? So the doublet fraction has to be less than about 0.1. And so for various values of tan beta, the picture changes slightly, but overall, the message is that the doublet fraction has to be very, very suppressed. The singlet fraction, you can still have a fair amount, so you can have about 40% singlet, and that's fine. and that's fairly generic for all values of tan beta. But the doublet fraction really needs to be suppressed, right? So that's what the fits are telling us, and that's what other people also found. I should point out that you have these narrow strips when tan beta is around 3 or 4, and that's because the coupling to fermions just switch sign, but become the right magnitude again. And so for that reason, they fit the data, but then these will turn out to be irrelevant. So the main takeaway message here is that it can be up to 40% singlet, but the doublet fraction has to be very constrained, right? So let's keep that in mind. So with that picture, here is the approach. So I've told you that these are the parameters that define the Higgs sector, right? And so we're going to study points that have a 126 GeV Higgs. And so what you can do with this parameter space is that you can exchange the soft masses for the Z mass, tan beta, and the singlet Bev S, or the mu term, either one, right? And then so you can calculate the tuning in the Higgs mass coming from these fundamental parameters. So we're going to use the same measure as the Jurich-Barbieri mechanism, right? And so you're going to calculate what the variation in the Higgs mass is when one of these parameters is varied, and then that gives you the traditional measure of fine-tuning. And the way these guys are going to be calculated is as follows, right? So for example, if you want to calculate the variation with respect to A lambda, then you have to calculate the direct variation plus the fact that A lambda feeds into the Z mass, tan beta, and the singlet Bev. And so you have to do this chain rule kind of thing, right? But in the end, you can do this, and then a number comes out, and that tells you what the amount of fine-tuning is. And so what we're doing is we're only doing this at tree level, and so that might seem odd because top loops are always important when you talk about the Higgs, right? But in this case, we are talking about very big tree level terms, right? So 300 GeV. And so because of that reason, loop effects are not that important. So we're just going to ignore that. I'll come back to that later. There are a couple of slides I can show you. But for now, right, everything is tree level, forget about the loops. And let's see what happens. So there are other constraints that are important, right? So for example, I just told you that tan beta needs to be less than 4 for electroweak precision test consistency. So we're going to stick to that bound. You can't have tachyons in the Higgs sector, right? So any points that have that are out. We're only going to focus on cases where the Standard model like Higgs is the lightest of the CP even Higgses. So this is not necessarily the case, but anytime where there's an even lighter Higgs than 125 GeV, you're talking about even more fine-tuning, right? So you're talking about two particles that are now far lower than what the natural scale of the theory is, and so that picture is probably very fine-tuned. So let's not worry about that, and we're just going to focus on this case. When you work with Lambda-SUSY, you also need to worry about the unrealistic minima of the Higgs potential. So the Higgs potential, right, so it has its minimization conditions, have 3 equations. They are all cubic in the Higgs web, which means that you have 27 different solutions to those equations. One of them is the correct one, where the Higgs web is 174 GeV, right? But there might be others which are deeper, which have a completely unrealistic number. And so you have to make sure that those minima do not actually sit deeper than your realistic minima, right? So we do that check, and since it's only at tree level, we only reject those points if the unrealistic minima are sufficiently deeper that we know that loop corrections are not going to change that order, right? So we're just taking this very safe approach where we know that the things we're throwing out are definitely out, even if loop corrections come into play.
So this wave can be a complex one.
Yes.
So that means you also minimize that imaginary decelluloid. Is there anything else? But can anything happen in that direction? Do you get a complex lambda out of that?
So we didn't look at that too closely, but that's certainly possible.
I'm just wondering.
Yeah. Right, and finally, you have to make sure that the charge stays above experimental constraints, right? So all these traditional constraints that you would throw in, we throw in. And so let's look at what the outcome of all this exercise is. So let's first look at a simplified picture, right? So we're going to look at this picture where tan beta is equal to 1. And that picture simplifies the process because then these off-diagonal terms go to 0, which means this heavier doublet is completely decoupled from the system, and your system reduces to just the Standard model like Higgs and the singlet guy, right? And so you're only looking at mixing between 2 fields, which is a lot easier, and you can make a lot of progress analytically. So Right, so you have the 7-dimensional parameter space. You exchange these 3 guys for the soft masses. You can fix your Higgs mass to be 126, and you can fix what your singlet fraction is that you want, and that fixes 2 other numbers, right? And if you also fix lambda, then there are only 2 free parameters left: this kappa term and the singlet valve. Everything else is fixed, right? And so the benefit of working with a 2-dimensional parameter space, of course, is that you can make 2-dimensional plots, which are easy to show on a 2-dimensional surface. So here they are. So they look fancy, so let me tell you what these are. So on the right side, you have the amount of fine-tuning as a function of kappa and S, right? And so darker colors mean more fine-tuned, lighter colors mean less fine-tuned. So you can see that generally lower singlet masses will lead to less fine-tuning, which makes sense, right? If your mass scales are lighter, things are less fine-tuned. And so the 3 plots are for singlet mixing in the Higgs. That's 40%, 15%, and 5%. The more interesting plots are the plots on the left. So these tell you which parts of the parameter space are allowed and which parts are ruled out by the constraints. So the white parts are allowed. The purple parts are where the minimum of the Higgs potential is an unrealistic minimum. So we definitely don't want to live in those parts. Right? And this green or dark gray regions are where one of the Higgses is tachyonic. So that's also out of the picture. And so you can see that as you decrease the amount of singlet mixing from 40% to 15% to 5%, you see that this tachyonic constraint just eats up your whole parameter space, right? And so here you could hope to live in one of these white spots, and that would land you in this not so fine-tuned region. When you crank down the mixing, that spot is no longer there, and you have to live up there, which means more fine-tuned. And if you crank down the mixing even further, then you can only live in one of those corners, and that means a lot of tuning, right? So the trend seems to be that as you reduce the amount of singlet mixing, your constraints grow stronger and stronger, and you're forced to live in more and more fine-tuned corners of your parameter space. Right? And so you can understand this intuitively, right? So think about the singlet fraction as the sign of some singlet mixing angle. That mixing angle is given by the off-diagonal term over the singlet mass term, of course, right? And so if you want this angle to be small, that just means that you want this ratio to be small, right? Which means you want these parameters, so A lambda or the singlet Bev, to be a lot larger than the Higgs Bev or the Higgs mass, right? So heavier mass means more fine-tuning, and that's the picture that comes out indeed. With regard to the constraint, so it turns out that the constraint that's the strongest is the constraint that the CP odd Higgs mass should not be tachyonic. And you can rewrite that in terms of the singlet fraction as follows, right? So this whole thing needs to be a positive number. And so if you have large mixing, which means S is some order 1 number, then this whole thing is some order 1 number, right? And so then to be positive, you just want S to be around the same size as V. As soon as that happens, this whole number is positive. Right? Whereas if your singlet fraction is really, really small, which means S is some really small number, that means this is some really big number, right? Which means this number has to be a lot bigger than this number in order for this term to stay positive, which means that your singlet Bev now needs to be a lot bigger than your doublet Bev, and this hierarchy of masses is fine-tuned, right? So that sort of makes sense. This picture that as you crank up the mixing, things should get more fine-tuned, it makes sense if you think about it like this. So there's one more region that I need to point out before I move on from this picture, which is that there does seem to be this very anomalous region in this picture. And you actually don't see it in this picture, it's around there. And even if I zoomed into that picture, I will not be able to see it. And so therefore, what I've done, right, so it sits around there. And so if you zoom into that region and make that plot bigger, then you see that there's actually a narrow allowed region that sits right above this gray band and right in the middle of this purple band. And so it seems to be very natural. So it's a fine-tuning of around 10%. It passes all the constraints, right? So we have this very counterintuitive patch of parameter space that seems to survive. But this region is slightly suspect because this region is where the singlet Bev is very low. So it's around 50 GeV, which means your mu term is around 100 GeV, right? And so you have really light charge nodes. There might be loop effects that can change the fit. Also, the Higgs potential in this region is very close to 0. And so loop corrections, who knows how they'll change the picture. So there is this picture that survives the constraints that we impose, but then there are all these tricky things with that region which suggest that maybe we shouldn't take it too seriously, but it's there. Right?
So it only shows up for large mixing. It shows up for all these.
So there's a different plot where you can see it better. So let me hold up that discussion until then. It shows up at all mixings, but it's, yeah, so you'll see it soon. So that was the 2x2 case, right? So tan beta 1, if you just look at the two particles mixing, then this is the intuition that it suggests. Of course, the realistic case is that the other doublet can also mix in, right? So the full sector is a 3x3 sector, and so we no longer fix tan beta at 1, we scan over it for its full range, and it turns out that the intuition that we built up from the 2x2 case, they all survive. And so everything I said is still true in the 3x3 case. Of course, it's less straightforward to see because there are too many parameters. And so we scanned over the parameter space and studied it. And I'm going to show you the results of that scan. So here is the most important plot in the talk. So this is the time to stand up and take notice, right? And so the left plots plot singlet, or the amount of fine tuning as a function of the singlet fraction. And the three are for different values of tan beta. So this is tan beta between 1 and 2, this is between 2 and 3, this is between 3 and 4, right? And on the right, we have the same plot, but now for the doublet fraction instead of the singlet fraction. And so what the points are that the pink points are the points that pass all the constraints, all the other constraints, but are not consistent with the fit to the Higgs couplings. So those are the points that you might have said were okay before when you just knew the Higgs mass. But now that we have constraints from the couplings, those pink points are no longer reasonable, right? And the points that are still consistent with the Higgs fit are the points in green. So you can think about it as, right, so all these points were possible. The Higgs mass cut it down to the pink points. The Higgs couplings fit cut it down to the green points. And so you can see this, and so there's this other color, right? So there's this yellow region too in the first plot, and that's exactly this anomalous region that I was talking about. So those are the points where the singlet web is fairly small, and you get very natural points that fit all the cuts, including the Higgs fits. And so you can see that they're all for all possible singlet fractions, right? So that's the answer to your question. So yeah, so they show up for all possible mixings. But they're categorized by this narrow region where the singlet web is very small. And so the Higgs potential is also very small. And so loop corrections might completely change that picture. So we can't say anything definitive until you do a full loop analysis.
But maybe you have some signal there. Like
Well, you can have some signal there, definitely.
charging.
Yeah, so light charging is definitely. So yeah, so that is the high promise signal. Right, and so the trend is there for all plots to see, right? So the trend is that as you further constrain the doublet mixing fraction or the singlet mixing fraction, then you're forced to live in a region of greater and greater fine tuning, right? So if I force you to go left, you have to go up, right? Which means that as you measure these couplings better and better, and as you constrain the doublet fraction and the singlet fraction better and better, you will force your theory to be more and more fine-tuned, and that's true for both the doublet fraction and the singlet fraction. And so the trend you see is that as you increase tan beta, that statement grows weaker, but that correlation still persists. Right? And so tan beta is an interesting case. So what increasing tan beta allows you to do is that it allows you to reduce your tree-level Higgs mass, right? So the tree-level term is lambda squared cosine squared 2 beta. So if I could increase tan beta, then I would be decreasing that tree-level mass. And so I have a smaller cancellation. I don't start at 300 GeV, I start at a smaller number. So getting to 126 is a smaller cancellation, so it's less fine. And so you can sort of see that here, right? So this is the tree-level mass before mixing, and this is the singlet fraction. And the tuning color coding goes as red is the most natural region. Green is more, well, so this should say 10, 10 to 30, and 30. Anyway, so the red is the most natural region, green is slightly less natural, blue is fine-tuned, right? So if you start with a huge tree-level mass, then you're clearly forcing yourself to be tuned. If you decrease your tree-level mass, you can be more and more natural. Right? So likewise, as you constrain your singlet fraction, you are forcing yourself to be in a more and more tuned region. So this is just the earlier information replotted in a different way. And so this is all for lambda equals 2, right? So all this variation is coming from different sources of tan beta. So you might wonder about how things change when lambda is varied too, because so far I've just done everything with lambda equals 2. And so we also try to study how things change when lambda itself is changed, right? And so here is lambda between 1.9 and 2. So this is essentially the plot I showed you earlier. If I reduce lambda, then what you see is that as I reduce it from 2 to 1.6 to 1.4 to 1, the green regions migrate lower and to the left. The pink regions also migrate lower and to the left, right? And so what you're doing is you are decreasing the tree-level Higgs mass, and so it's easier and easier to get a 126 GeV Higgs without any fine-tuning. And so if you reduced your lambda low enough, and by low enough I mean around 1.5, by that point things are completely natural, right? So you have all these green points, and that go below 10, and so you can live with no mixing with the singlet, just the tree-level mass gives you the right mass. And so even if you could reduce the singlet fraction to close to 0%, you're not saying anything about the fine-tuning that goes in, right? So your other option is to decrease lambda if you don't want fine-tuning. But of course, if you decrease lambda, then the tuning with respect to the stop masses, you give up, right? So what you gain in the Higgs mass naturalness, you lose in the heavy stops naturalness. So there's some trade-off. So talking about stops, right, you can also worry about how including stop loops will change the picture. So here is one illustration of how it does. So on the left is a plot that I showed you earlier for tan beta between 2 and 3. This was completely tree level. Right? On the right, we've done the same analysis, but we've also added stops. So stops are now so in this picture, stops are at 1 TeV. There's no mixing, right? So 1 TeV stops, no mixing, changes the picture by that to that, right? So you can see that there's not much of a difference. It's the same picture, same correlations, same shapes. The only thing you can say is that fine-tuning goes up slightly, right? So if you look at the very minimum of this region, then this is around 60, this is around 80. So including stops has pushed up your fine-tuning by a factor of 1.3, which is nothing, right? And so that's because a 1 TeV stop gives you a contribution to the Higgs mass that's around 80 GeV, compared to the tree-level mass of 300 GeV, that's nothing, right? And so of course your tree-level mass is now slightly higher, which means you need a slightly bigger cancellation to get a 126 GeV, but not much.
But don't you need less lambda or again?
No, so this is for lambda equals 2 again,
Oh, you
right? So you fix lambda equals 2, now you also add the stops, which means your tree-level mass is now slightly higher. Yeah, yeah. So adding stops will make the picture worse because the requirement here is the opposite of the MSSM, right? In the MSSM, you want to raise the Higgs mass because its natural scale is too light. Here you want to lower the Higgs mass because the natural scale is too heavy. So adding stops is actually bad, and it pushes you in the wrong direction. But it doesn't push you in the wrong direction by too much, right? So you can have a TeV scale stops, and everything I've told you remains the same. You can have several TeV scale stops, and you would have to go a long way before fine-tuning changes by even a factor of 2. So in Lambda-SUSY, generally, you can forget about stop loop corrections. And the tree-level contributions are so big, right, that stops won't make a difference. And so with that, I've actually said everything I wanted to say. So time to summarize, right? So these Lambda-SUSY models, when I first ran into them, I thought they were really fascinating because they allowed you to raise your weak scale from your naive Z mass up to this massive lambda wave, which is around 350 GeV, right? Which means your fine-tuning measures are all improved by this factor of lambda over G squared, which for lambda equals 2 can be as large as 10. So you've essentially found a way of improving your fine-tunings by an order of magnitude. And so this is a very attractive thing in light of the fact that we have not seen any superpartners. In fact, we have not seen any stops, is the biggest concern, but superpartners in general, right? So that's a big issue. And this somehow slightly alleviates it by pushing the scale we expected up by a factor of lambda over G. not a factor of around 3 or 4 is not much, but when you're talking about actual numbers and actual energy scales available at the LHC, that's a big statement, right? So pushing the natural scale for stops from 300 GeV to above 1 TeV is a big accomplishment. And so this somehow does that. So the flip side of it is that your natural scale for Higgs is also too heavy, and you need to cancel it down to 126 GeV, which is possible to do. You mix it with a singlet, and you can accomplish this easily. But the thing we found was that if you also take into account the information we have about the Higgs couplings, then that mixing is not so easy to get and still remain consistent with all the measurements. So now your tuning goes down from 10%, which was the story from just knowing the Higgs mass, to about 2 to 3% tuning. So lambda equals 2, if you want to be consistent with everything, is now tuned at percent level also, which looks bad, right? And so the best you can do is maybe not live all the way up to lambda equals 2 and push it down to lambda equals 1.5. So there, the Higgs mass tuning is very natural. You lose a little with respect to the stops, but that's lose a little bit, but gain some picture. There is a small region that seems to be suspect with respect to vacuum stability and loop corrections, but it survived all our points, right? It survived all our fits. But the general trend that we saw, that by further reducing the constraint on the Higgs mixing with the doublet or the singlet, you can further make stronger statements about the amount of fine-tuning in the picture. In Lambda-SUSY, it holds generally. So either with more data, we will push it to more fine-tuned regions and eventually kill it, or we are possibly looking at actually finally finding some deviations in the Higgs couplings if things are still to be natural. And so that was the outcome of our study in Lambda-SUSY. So I have backup slides, but I don't think we want to go there. So thanks.
So we have time for questions.
Yes.
Can you say more about the mass scales of the Higgses that you're expecting? When you push your lightest one down to 126, where are all the others sitting?
So 350 is the most natural scale, right?
So there
And
should be a couple there?
So around
or
there. Yeah.
how many? Would you get there to be more than one sitting there?
Could be. I mean, just the second doublet and the singlet, and their natural scales are at 350.
Well, would they be coupling to mostly? I mean, are they coupled the same way as the standard model Higgs, where they do mostly
So
like
the singlet
heavy
doesn't
things?
couple to anything, right? And so the singlet could actually be a lot lighter than 125, and we would have never seen it unless it mixes somewhat with one of the doublets.
Doesn't couple with anything?
Not in the
Say like maybe a dark matter candidate?
So the Simlino is a dark matter candidate. The singlet, I mean, it can couple to, well, so I should take that back. So it can couple to the fermionic component, of course, right? So you have this kappa coupling, which was S cubed. So a singlet Higgs can couple to singlet fermions. So that vertex is allowed. And depending on what that number is, that is going to be big. Right, so there are just two couplings allowed for the singlet, right? So it's this one and this one. Right, so if it's, I guess if it's heavy enough, you can go to 2 Higgs bosons. If it's too light, I mean, you can definitely go off shell.
Well, if it's too heavy, well, you said it's 350, and so that's more than twice the standard models, and then
Yeah.
what
So
you'd be
you can have
looking
that.
for is 4 Higgs resonances at 350?
Well, how do you produce them though? I mean, the production will also be suppressed by, like you definitely can't go the usual way of gluons or gauge bosons. But yeah, if they were produced, they would either decay to Higgses or Simlinos. But you would probably not produce them that way.
The problem is you can't produce any of them.
Well, the second doublet you can, right? So
Where are
there's
those
this
sitting
big
at?
edge, and that second doublet should also be at 350. And so we didn't look at that very carefully, but that definitely couples to standard model fermions, right? So it's a doublet, it's an SE2 doublet,
What would that decay to?
and so that would probably decay to a couple of B's, the same as the Higgs, right? So the bottom U kappa is, well, if it's heavier than twice the top mass, you would also do twice the mass.
So if it's at 350, then you only see a resonance in the ET bar and the BB bar system. Yeah. production cross-section?
We don't know what the production cross-section is. We don't know what the mass is, right? So 350 is a ballpark estimate. You can make it heavier, you can make it lighter.
Should the production cross-section be at the same order of a Z prime, or would it be less?
So I guess you would produce them the same way as the Higgs, right? So gluon group. So you have a top loop and then the top loop this.
I would guess all the current limits on Z primes, Z to TT bar and Z to BB bar would be directly applicable. Because mostly it's just acceptance.
That I haven't thought about. That might be possible. So I thought about all these heavier Higgs searches that the LHC people do.
And if
And
it's
so-
light like 350, you're better off going with the tevatron of the LHC.
Mhm.
Because the LHC will blow it out of the water at 2 TeV, but at
Right.
300 and 400, you're better off with the tevatron.
Right. Yeah, so I did look at the LHC searches for this heavier Higgses, and their bounds are strongest for large time data, right? And so, which is not this case because here you can't go above 10 minutes for. So with that search, this was fine. I don't know about this in practice. That would be interesting.
So is there. So did you look at the neutralino sector, and then what are the typical masses for the neutralinos? Because now suppose if you somehow we find a way to search for these neutralinos and charge in the period, then can I see the existence of this singling or some?
Probably. I mean, depends on.
Because your S is kind of.
Yeah, so
kind
S
of
is all
wide.
over the place, but S.
But suppose you take this more natural scenario and S seems to be constant, so that makes your neutralino mass matrix you find some lower masses.
Yeah, so I mean, you can always make the Bino lighter, right, and that's going to be the neutralino. But generically, that's true. So in the singlino mass matrix, right, so you have the usual, right, Bino, we know, Higgs, and the singlino. And so the entries here are mu, right, usual. This is kappa over lambda mu, so usually this is smaller. But if this is the lightest guy, then you get a lot of mixing between these two. And then you can actually have this coupling, right? So Higgsino, singlino, Higgs, and you can get a big signal at direct detection. And so that actually kills off a lot of these lightest singlino guys.
And so that's also interesting, you know why? Because suppose you produce Higgsino somehow, and then Higgsino give you a good signal. Some singlino is your light waves. That means Higgsino Higgs singlino. So that means your
And the coupling is lambda, right, which is huge.
BB bar. So that's a good signal. So even at the LHC, you can find the BB bar plus missing energy or something like that. That means you can missing energy plus Higgs. That would be interesting.
So Bhaskar, this means you are asking for 5 by 5?
Huh?
You're asking 5 by 5?
Yeah, now it's a 5 by 5. That is written down. We know.
BB
Yes, you have this new guy,
There's a lot of
the
searches
singlino,
for BB bar plus MET, and those are just the Higgs searches.
Yeah, but here, for
And that's the
example,
heavier Higgs search, right?
yeah, but now it's a different thing. So BB bar gives rise to a Higgs mass. That means you demand that BB bar to be in the Higgs window, and then you have a MET. So that's a good signal for this machine. So this BB bar would be the Higgs window. Higgs mass window.
I think in any case, even the invisible fraction of the Higgs rules out these large mixing scenarios.
Yeah. In fact, there are many.
But yeah, you can think of a lot of things that
It's interesting.
should be visible with this coupling.
Yeah.
But this mess with your,
I never thought about it.
I haven't thought about it much
actually
either,
like
I
it.
should say, so.
Strava could be heavier, so don't worry about the missing direction ratio for Higgs.
What was that?
What could be heavier?
Well, I mean, the dark matter could be heavy, so Higgs doesn't decay into it.
No, actually
Well,
this is
and-
interesting.
Right, so in this most natural regions, right, mu is around 100.
If you had a heavy
Lambda
signal,
actually
you can
big
produce
lambdas.
them, and maybe some decay will give you signals.
Yeah, so it's kind of on the lighter side, right? So that's why I'm raising this question. Right? The Higgsino is next to Singlino, and Higgsino will decay into a Singlino by emitting a Higgs.
Yes.
So that's a.
Yeah.
More questions?
Shouldn't this affect your relative density due to the couplings at 3 cell?
Well, relative density has lots of moving parts.
Yeah, so it depends on,
Lots of moving parts.
Well, I know, that's what I'm asking. I mean, in some sense, you've got a set
Yeah.
of criteria that you put up.
And
Yeah.
usually, see, your cross section is usually on, always on the smaller side, but here probably he has a.
yeah, so here the cross section is going to be too big to get the right density.
Exactly.
It's definitely going to overshoot that.
So you're not gonna get them. So do you put that on as a constraint, or are you just ignoring it?
Well, I mean, I didn't think about the neutralino side at all, right? But what I could do, but for example, could be that I could make it mostly Bino. So if I make it 60% Bino, for example,
Just,
maybe
You don't think it's gonna make?
no, it's not a problem. But what you will do, you dilute the thing by bringing a little bit more Bino or Bino.
yeah. So your Bino mass is still a free parameter.
Free
right?
parameter.
There's nothing that much
So it's not gonna change,
So
right?
that's
Yeah. So you can always cook up a scenario where you get right.
Doesn't buy you much. Okay.
Yeah, yeah.
Well, if no more questions, let's thank Bibhushan again.